Hi everyone, this is Mr. Hall and this is a really quick video about moles. I'm going to talk about moles in two videos because I think moles is actually quite hard, and in order to kind of give it the justice it deserves, I'm going to break this into two. So today I'm going to talk more about what a mole is and how you do some basic calculations with Avogadro's constant, and then in a future video I'll talk more about the traditional calculations of moles, MR and mass, which you commonly get in exam situations. This, for those of you who are studying sort of AQA or GCSE or any sort of that kind of study, this is where quantitative chemistry gets quite tough, because your understanding of moles is directly going to impact your ability to do limiting reagent, reacting masses, stuff like that. So getting your understanding of moles right from this position onwards is really important. So today there's just two things I want to talk about. I want to talk about what is meant by 1 mole of a substance, and I want to talk about how to calculate the number of moles, atoms and molecules for substances using MR data. So first of all, let's think about some balls first of all. So first off, if we have a bowling ball, now the average mass more or less of a bowling ball is around 5,000 grams or 5 kilos. However, there are lots of different types of balls out there, all of different masses. Okay, so you can have a pool ball, which has roughly a mass of about 500 grams, and then you can have a golf ball, which has a mass of 50 grams. Okay, important thing is that they're all balls. They just have different masses. Now, what I could do is I could, instead of just having one of these balls, I could have lots of these balls, okay? So for example, I could check how many balls I have by counting them or by determining the mass. So if I think about having 10 bowling balls, okay? Now 10 bowling balls, each one was 5,000 grams. So if I have 10 of them, I now have 50,000 grams worth of bowling ball. I could also have 10 pool balls, with each one being 500 grams. So 10 of those is 5,000 grams. And I could have 10 golf balls, and 10 golf balls, that's 500 grams because you've got 10 lots of 50. So you can see that in each case, each individual ball weighs more or less than another. Therefore, if you have 10 lots of each, the difference in mass gets greater or smaller. But the key thing that they all have in common is that there's always 10 of each ball. Now, you can actually use this idea of different masses of balls with elements, okay? So instead of a bowling ball, we could have oxygen, which has got an atomic mass of 16, or we could have carbon, which has got a mass of 12, or hydrogen, which has got the mass of 1. And the idea that you've got different masses of each kind of quantity, but the same number of atoms is a very, very useful when you're trying to think about moles. Now, let's apply this to atoms. So if you think about hydrogen, hydrogen has a relative atomic mass of 1. So we say that 1 gram of hydrogen is 1 mole. And we could say the same thing for carbon, where carbon, if I have 1 mole of it, it's 12 grams because it's an atomic mass of 12. And then with oxygen, an oxygen atom has a relative atomic mass of 16, so 16 grams of carbon is 1 mole. Okay, so the important thing is that before I go into kind of more depth about what a mole is just like a quantity of something, all right, like a pair or a trio, and I'll talk more about that in a minute. But the key thing is for 1 mole, it's basically the same as the atomic mass of any element. Okay, so that means that if I have 1 gram of hydrogen, which is 1 mole, that'll contain the same number of atoms as 12 grams of carbon or 16 grams of oxygen, and it will also contain the same number of atoms as 23 grams of sodium or 32 grams of sulfur, because you'll notice that each of these masses I'm mentioning, it's the same as the atomic mass that you can find on your periodic table, okay? And the same as 35.5 grams of chlorine as well. So now we use words to account for groups of substances all the time, and you probably use it in regular everyday speech. So for example, you could say I have a pair of something or a couple of something, like, which is 2. You could say I have a trio of something, like what trio of, I don't know, candy bars, which is 3. You could say I've got a quartet, maybe a quartet of musicians, which is 4. Or you could say I've got a dozen something, like a dozen eggs, which is 12. All right. Now a mole is exactly the same kind of thing. It's just a number of something. We just say we have a mole of something. Now we tend to use it when we're talking about atoms because the number is very, very big, and I'll talk more about what that number is in a second. Okay, so the number of atoms in 1 gram of hydrogen, 12 grams of carbon, and 16 grams of oxygen is very, very large. Remember, for all those values, all these is for 1 mole. Okay, so the number is huge. In fact, there is this many. Okay, so it's an absolutely humongous number. It's absolutely huge. Now, we don't often use this number in this form because it's quite difficult to use. Therefore, we approximate it. Therefore, you have this many atoms in 1 gram of hydrogen, 12 grams of carbon, 16 grams of oxygen, 32 grams of sulfur, and so on, anything which is equal basically to the AR. Now, that number is called Avogadro's number, and it's usually written as 6.022 times 10 to the 23. Basically, it's standard form, all right, because it's so big. So when you're doing calculations with regards to moles, you'll often be asked to do it in standard form because the numbers are so big, all right? Now, the number is too big to be used sensibly. So you often don't say, oh, I've got 6.022 times 10 to the 23 atoms of hydrogen. You never do that because it's ridiculous. It's much easier to say I've got a mole of hydrogen, or I've got 5 moles of chlorine, or 6 moles of carbon, whatever. That's a much easier way of doing it. Now, this number, Avogadro's number, it was named in honor of this Italian chemist Amedeo Avogadro, who lived sort of between the 18th and 19th century. Just a bit of interesting knowledge there. Now, let's talk about calculations. Now, 1 mole of anything is 6.022 times 10 to the 23. Therefore, if I had a mole of pesos, I would have 6.022 times 10 to the 23 moles of pesos, which would be quite a lot of money. If I had 5 moles of mangoes, I would have the number 6.022 times 10 to the 23 multiplied by 5, which in this case would be 3.011 times 10 to the 24 mangoes. Now, you can go online and you can find these kind of calculations of, you know, like how many Grand Canyons could you fill up with a mole of pennies and stuff like that, and they come up with some quite amusing sort of results, and that may be something you might want to search. But the idea of a mole, it's a humongous number, and that leads us on to this equation. Now, this equation, what it tells us is you've got moles on the bottom left, number of atoms or molecules at the top, and then you've got Avogadro's constant on the right, which is this number here. And what you need to be good at is using this equation triangle for any problem that comes your way. Okay, we'll start with some basic ones just to kind of work out mole, and then later on we'll work out this. You'll obviously never have to work out Avogadro's constant because it's a constant and it never changes, and that's quite a useful thing. This always stays the same. Sometimes we give it the symbol AV to represent this as a constant, Avogadro's constant. Okay, so let's go for some examples. How many atoms are in 1 mole of zinc atoms? Now, if you think about the equation triangle, I'm trying to work out the number of atoms, which is at the very top here. So therefore, my calculation, I'm just going to put a hashtag for number, is going to equal mole multiplied by Avogadro's constant, which I'm going to give the symbol AV. This is that number. The mole here is 1, so it's 1 times Avogadro's constant, which is the same as that number. So it's going to be that. Okay. If I'm asked for the moles, the atoms rather, number in 1 mole of carbon atoms, same thing. Okay. I'm working out the number of atoms of carbon, which will equal mole multiplied by Avogadro's constant. Avogadro's constant is always 6.022 times 10 to the 23. My moles in this case is 1, so it's 1 times Avogadro's constant, which is 6.022 times 10 to the 23. So it doesn't matter what the atom is. It doesn't matter if it's hydrogen, carbon, oxygen, neon, iodine, doesn't matter. 1 mole of it is always going to be 6.022 times 10 to the 23. Now, if you've got the question of how many atoms are in 3 moles of hydrogen atoms, that's slightly different, okay? Because now I have to use this equation still, which is the number of atoms is the same as mole multiplied by Avogadro. But my mole now is 3. So I need to times Avogadro's constant by 3. So 3 times 6.022 times 10 to the 23, and that gives me 1.81 times 10 to the 24. Okay, so that's some kind of basic calculations. It can get a little bit trickier. So for example, the number can also apply to the number of molecules or atoms in a substance. It'll be a tough question if you get this, but sometimes it does come up. So for example, if I've asked for how many molecules are in 1 mole of H2O, that'll be 6.022 times 10 to the 23, because it's the same idea of number equaling mole multiplied by AV, and this is still 1. So it's 1 times Avogadro's constant, which gives you 6.022 times 10 to the 23. But if I've asked you how many atoms are in 1 mole of H2O, that's a very, very different question, because we know that from the formula, water contains 2 atoms of hydrogen and 1 atom of oxygen. So it's 3 atoms in total. Now, if I want to know how many atoms are in a mole of it, I now have to do the number of atoms, which is 3, and I multiply that by Avogadro's constant to get the answer. So it's going to be 3 times 6.022 times 10 to the 23, which gives me 1.81 times 10 to the 24. So that's some trickier problems which you might get. Now, you might be asked to do some division. This is quite rare, but it sometimes happens. So for example, you might be asked for the number of moles in something. So the question here is, how many moles does 6.022 times 10 to the 23 molecules of Cl2 contain? Now, if you look at our equation here on the top left, mole equals the number of atoms or molecules, I'll just put hashtag, divided by Avogadro's. Now, in this case, I've got 6.022 as the number. So it's going to be 6.022 divided by Avogadro's constant, which is, in this case, the same number, so it equals 1. So that many molecules is 1 mole, which is what you'd expect. Here's another problem. How many moles does 3.011 times 10 to the 22 molecules of Cl2 contain? Again, my equation, I look at the equation triangle, mole equals the number of atoms or molecules, which I'll put as hashtag, divided by AV. In this case, the number there is 3.011 times 10 to the 24, and I divide that by Avogadro's number, okay, which I'll put as AV. So I do that calculation, which I've just explained, and that gives me the number 5. Okay, you just have to kind of pump it in your calculator and you get the right answer, but always show you're working, always show you're working. And then finally, tricky one here, how many moles of Cl2 does 4.8176 times 10 to the 24 atoms of chlorine contain? Now, this is a tough problem. Now, if you think about it, I need to work out moles of the chlorine atoms first of all. So moles will equal, as we've always mentioned before, hashtag divided by AV, and that's from the equation triangle over here. So that would equal 4.8176 times 10 to the 24, you can just about see that, divided by Avogadro's constant, AV. So if I do that calculation and I put the numbers in, that'll give me 8 moles of chlorine. Now the important thing here is that that gives me the number of atoms of chlorine. So that's individual chlorine atoms, but it doesn't tell me the moles of Cl2. Now, if I've got that many moles of chlorine atoms, to work out the number of chlorine molecules, I just have to divide that by 2. And that's 8 divided by 2, which equals 4 moles of Cl2. Tough problem, but you might get it, okay? And that's it. So I hope that's been useful. In the next video, which I'm going to make, it's going to be more about moles, mass, and MR, and maybe some 2-step problems as well.